Consider the following problem. The digit 3 is written on the right of a certain 2-digit number to make a 3-digit number. The new number is 777 more than the original 2-digit number. What is the original number?
Let's consider the digits to be A and B, where A is the tens digit and B is the units digit. Now let's look at the second number. A is the hundredths digit, B is the tens digit, and 3 is the units digit. This hundredths digit can be considered as 100 times A. This tens digit can be considered as 10 times B, and this is just 3. So, this whole number can be written as 100A plus 10B plus 3. We can do the same thing on the other side, writing it as 10A plus B plus 777.
We can then minus 10a from both sides, leaving us with 90a plus 10b plus 3 equals b plus 777. From here, we can minus b from both sides to get 90a plus 9b plus 3 equals 777. And finally, we can minus 3 from both sides to get 90a plus 9b equals 774.
From this point, we can divide by 9 to get 10a plus b equals 86. You may be able to recognize this structure 10a plus b from before. In fact, it's the same structure we used to write out the 2-digit number ab when we multiplied the tens digit a by 10 and the units digit b by 1 to get 10a plus b. So in fact, our answer is that the 2-digit number ab is simply equal to 86.
Now consider this problem. Find a number less than 100, which is increased by 20% when its digits are reversed.
Let's start by looking at the increase in 20%. We can consider this as equivalent to multiplying the original number by 120% because it is simply 100% plus 20%. 120% of a number is the same as multiplying a number by 1.2. So, we can say that some number AB multiplied by 1.2 is equal to its reverse, BA.
As we did in the previous problem, we can represent AB as 10a plus b all times by 1.2 equals 10b plus a. We can then multiply this out to get 12a plus 1.2b equals 10b plus a. From here, we can minus a from both sides to get 11a plus 1.2b equals 10b. And finally, we can minus 1.2b from both sides to get 11a equals 8.8b.
Now, we can divide by 11 to get a equals 0.8b. Then we multiply by 5 to get 5a equals 4b. We now know that there are two digits a and b such that 5 times a is equal to 4 times b. We know that the lowest common multiple of 5 and 4 is 20. So, 5 times a has to equal 20 and 4 times b also has to equal 20. Therefore, we know that a is 4 and b is 5, so the original 2-digit number is 45.
Finally, does there exist a 2-digit number, AB, such that the difference between AB and its reverse, BA, is a prime number?
As we did before, we can write AB as 10A plus B, and we can write BA as 10B plus A. We can simplify this to get 10A plus B minus 10B minus A, or 9A minus 9B. So we know that the difference of AB and BA is 9A minus 9B. We can factorize this, taking out the 9 so that we can write it as 9A minus B. We now know that for any digits A and B, the difference of AB and BA is always a multiple of 9. And the definition of a prime number is a number that only has factors of 1 and itself, which means that it is impossible for it to be prime, and in fact we know that it will always be a multiple of 9.
The main takeaway from these problems is that you want to break down 2-digit or 3-digit numbers such as AB and ABC into what digit they are really representing. So for AB, you'd break it down into 10A plus B, and for ABC, you'd break it down into 100A plus 10B plus C.
From this point, you can work with this to solve any equation, and remember, ideally, you want to find an answer in the form of 10A plus B or 100A plus 10B plus C so that you can plug the values back into the original number. Alternatively, you could solve for A and B as we did in some of the questions.
Thanks.